Hi, welcome back to lab session of microcontroller programming. So in this video we'll see how to implement CAN internal loopback in STM32. This in this STM32G431RB MCU and in this Nucleo 64 evaluation board we have got a peripheral as CAN FD. Here FD stands for flexible data rate. So this CAN FD is the extension of the classical CAN, that is the CAN 2.0 protocol. And this CAN FD is the successor of this CAN 2.0 and it efficiently supports the distributed real-time control with a very high level of security. That's why it has an added benefit over here. This CAN FD was developed by the Bosch and it was standardized as this ISO 11898-1 and it is suitable for the industrial and automotive and general embedded communications. Now the features for this CAN FD are it is compatible with the classic CAN protocol also, and it is able to send or receive the CAN messages according to the standard. It has an error checking improvement which is based on the CRC 21 bits. And the prioritization of the messages and the guarantee of latency times are the added features which are there present in this CAN FD. Also, the CAN FD format, the data message format is like the data is sent into packages, into messages as it is shown in this figure. So a message in this can be divided into these three phases, like this first arbitration phase, which includes a start of frame. This is a 1 byte start of frame. Then we have an ID, number and the other bits that indicate the purpose of this message, like is it a supplying or requesting data message, and the speed and the format configuration. These 3-4 parameters are included in this first phase, that is the CAN arbitration phase. That is start of frame, this 11-bit identifier. We can either have a 20-bit identifier as well. Then there is this bit which represents the purpose of message, and the speed and the format configuration, whether it is like CAN or a CAN FD. Then the next is CAN data phase. In this there is the data length code which indicates how many data bytes this message contains. Then the next thing in this CAN data phase is the data the user is wishing to send. Then there is a CRC bytes, like here 17 or 21-bit CRC, and there is a dominant bit. Then the third phase is the CAN FD arbitration phase, again after the data phase. Then in the second arbitration phase, it contains the acknowledgement bit which is transmitted by the other nodes on the bus, and that is if at least one has successfully received the message which we have sent. And then we have a end of frame bit. When no message is transmitted during the IFS, the objective is to separate the current frame with the next frame, so that there will be a distinction between the first frame and the second frame which this CAN is sending. In case of this 20-bit identifier frame, it is similar to the CAN FD frame when adding an 18-bit identifier after the bit ID in the first arbitration phase. So here, instead of this 11-bit identifier, we can send a 29-bit identifier as well. Now the improvements and benefits which we are getting with this CAN FD above this CAN 2.0 is like its development responds to the need of communication networks that require a higher bandwidth. So the applications where we need a higher bandwidth, in that case this CAN FD is useful. And this need is fulfilled by this CAN FD by having up to 64 bytes per frame, which makes it compatible for a higher bandwidth, and by its possibility to increase the bitrate to up to 8 times faster during the data phase, and to go back to the normal bitrate during the second arbitration phase. The data rate integrity in this CAN FD is ensured by the CRC, that is this checksum of payload, which is of 16 bytes and based on the 17-stage polynomial. And also a 21-stage polynomial is used to checksum the payload between 16 and 64 bytes. So the difference between the frame formats for this classic CAN and this CAN FD is not much, just that at the end it has a added CAN FD arbitration phase which was not present in this classical CAN. in this classical CAN we just had a end of frame bit, but here in CAN-FD, CAN-FD arbitration phase has been added, in which few more bytes are there which are transmitted along with this frame. So this CAN-FD offers a possibility to configure this two sets of acceptance filters. One is for the standard identifiers and one is for the extended identifiers. That is to store or reject the received messages. Now up to 128 filter elements can be configured for this 11-bit standard identifier, and up to 68 filter elements can be configured for this 29-bit extended identifier. So here the start address of this 11-bit filter section is configured via this FL SSA register, FL FDCAN DFC register, and this 29-bit filter section is configured using this FDCAN DFC register. So this 11-bit filter and 29-bit filter has been supported with this FDCAN. So these filters can be assigned to the RX FIFO, that is 0 or 1, or to the dedicated receiver buffers. So when the FDCAN performs this acceptance filtering, it always starts the filter element with a 0 and proceeds to the filter list to find the matching element. So the user can choose if they want to enable or disable each filter element and configure the different elements for acceptance and this rejection filtering. So this each filter element can be configured as a range filter, that is to match all the messages within an identifier which is defined by the two identifier filters. Then we have a filter for the dedicated identifiers, that is the filter can configure to match one or two specific identifiers. Then we have a classic bit mask filter, which is there to match the group of identifiers by masking the bits of a received identifier. Now we'll open the CubeMX and start configuring the CAN. So here I have enabled the FDCAN pins through this connectivity option. So here we'll enable this FDCAN and we'll set it into this classic master mode, and also we have enabled this FDCAN interrupts, both 0 and 1. Here this FDCAN is configured as P8, 11 and P12. The other pins which you can see are the default configurations on this Nucleo 64 evaluation board. So this FDCAN transmitter and FDCAN receiver we have enabled here. Then in system view, in this FDCAN, there is a and then is clock configuration. This is fine. Then we have given the name to it. Now we can generate the code. Let's open project. So here, as you can see, our code is generated. So in this main.c, in this FDCAN handle type def is HFDCAN1. We have enabled this FDCAN1, and we have enabled this UART LP UART1, which is a debug UART. Now here we have defined the CAN filter. So we have used this type def for this. If you go to the definition of this, so this is available in this fdcan.h fdcan.h file. This is a structure in which all the parameters which we have to configure for this FDCAN filter are defined. like ID type, which specifies the identifier type. Then there is a filter index, which is there to initialize the filter. So this parameter must be a number between this 0 and this particular bit, and if it is a standard ID, and in this range if it is a extended ID. Then we have a filter type, so it is there to set the filter type for this particular FD can. So the value, if it is permitted only when the ID type is extended ID. And then we have filter config. This will have a value for the configuring the filter configuration. Then this is for filter ID 1, we will be setting the value for it, and this filter ID 2. So then the next thing is the header type def for the transmitter. So we have given the name as CAN-TX header, and this is the structure for this TX header type def. Here again this few parameters are defined, which will be setting up. Same way as the identifier type. Then we have the transmitter frame type, then data length, the data which will be sending, the length of that. Then there is a error state indicator, and then there is a bitrate switch. And we have to configure the FD format also, like the transmitter frame will be transmitted in classic or FD format. So in this STQMX we have selected the mode as classic master. So here we will be selecting the classic mode. Then we have the transfer event for this FIFO control, and then message marker. Then the next thing is this receive header type def. That is, here also there are few parameters to be set up, like the identifier, then the identifier type, then the receive frame type, again the data length. Mostly the parameters are same for this receive header and transmit header. Then error set indicator, bitrate switch, and there is the FD format. Again it will be classic in this case. Then this receive time stamp is there, which is the counter value which is captured on the start of frame reception. And there is this filter index, so it can be either for a standard ID or extended ID. Then it is there, this filter matching parameter is there to match the filter which we have set while transmitting. So it specifies whether the accepted frame will match any received filter or not. The acceptance of a non-matching frame may be enabled via the config global filter function. So this parameter can be either 0 or 1. Then we have defined two buffer, one for transmit data and one for receive data. So we are transmitting these two elements here. So in the main, the first thing we have to do is the CAN filter initialization. So in this is a structure which we have defined here. So inside this structure, all the parameters will be setting one by one. Like for filter ID 1, we have given it as 0. Again for filter ID 2, 0, so that it can detect all the filters or received filters available in the network. Then filter index we have set it as 0. Then next is filter type. So here we have set it as filter mask. So this filter mask is the classic filter as we have selected in the STQMX mode. Then the next thing is the ID type. So here we have selected the standard identifier. Then for the filter configuration, we have set it to FDCAN filter to RX FIFO. Then for this, then we have called this config filter function, where we have given the type def, that is for CAN1, and The second parameter for this is the filter configuration, which we have set here. So this is scan filter, which we have set here. And this filter config is given as Rx FIFO. It is set to 0. If the filter matches, then only it will receive the data back to the particular node. Then the next thing after initializing the scan filter and setting up all these parameters for this is to start the module. So for this we have called this function, which is HLFD can start. So for this scan1, so in this function we'll see. So in this we are checking if the status is ready. If it is ready, then we are starting it, and this function will return success if the device is ready to receive it. We have in this file the error codes are already also defined. Then we have given a delay of 1 second after starting the module. Then in the while loop, we have set the parameters for this transmitter header. So the first parameter is this data length, which we have to send. So in this case we have set it to 2 bytes. So we can see the definition. So this 2 bytes mention the 2 bytes data field. Then the next parameter is the identifier. So here we have given the identifier as 04. So in the definition we can see what it means. So in this file, so 04 for this identifier is with what we have set. And then the next parameter is the identifier type. So we have selected it as standard ID. Then the next is the FD format. So as we have selected as the mode as classic master, so the FD format is classic. Here you can see this is the type def for this classic mode. Then we have called this function which will be transmitting. So this is add message to transmit FIFO, and here we are giving the type def for this FD-CAN. Then we are sending this transmit header and then the data which we have to send. So this is the function where all the parameters, the frame type, data length, bitrate switch, FD format, the transmit FIFO control, everything we have checked. And whenever the status is ready, and will be the receiving node, if it is ready to receive, then we will be transmitting it. First we will be checking the ID type, that is the identifier type. Then for receiving, we will be checking if the receive FIFO level, if it is greater than 1. So if it is any value, if it is greater than 1, then it will receive it back. If it is in case if it is less than 0, then this receive function won't be working for it. So this receive FIFO value has to be 1 after it receives a certain data. So this receive FIFO we have given here. So this is the FIFO for receiving the messages. So its value should be incremented once it receives the data. Then if it is greater than 0, then we have called this receive function. In this is receive FIFO, the header, and the received data will be saved. Then in this, these are the receive address where the data has to be sent, then the byte counter, and the data. So we are transmitting the data and on the same, and at the same time we are receiving it. So in this way we have implemented this CAN internal loopback to test for the functionality and the reliability of this FD CAN. So we'll save it and build it. So no errors, it's fine. We'll flash the code onto the board. Okay, done. Now we'll check in the debug mode. So here, this is the received data buffer, and this is the CAN receiver header. These are all the different registers in which we have given the particular values to initialize this CAN module, like in this CREL register and CCR, all the different registers. And in this CAN RX header, this identifier and identify type, data length, everything. And this finally, after receiving the data, it will be received in this buffer. So we'll run it. So here you can see we were transmitting these two elements, that is CD and AC. As you can see, CD and AC we are transmitting, and we are receiving it back in this buffer as CD and AC. So here this CAN internal loopback is functioning fine. So we have tested this CAN functionality in this. So this is fine. We have received it, and here you can see the identifier which we had mentioned, that is 04 is there. Then the data length we had mentioned as 02. Then the filter index is 3F, and again the filter matching frame is 01. So it has matched to this frame, and then it is receiving the data. So what we are transmitting, we are receiving here back. So this CAN internal loop back testing is done here. So let's close the debug mode. So same ways you can implement the CAN protocol in this Nucleo 64 board or in this STM32 MCU in different modes also. This was a example for a CAN internal loopback functionality. So thank you for watching this video. Thank you.